Let's do a couple more examples of using reduction of order to find a second solution to a linear differential equation. Okay, so here we have a homogeneous second order linear differential equation. And we have one solution here, so you can check if you want that x squared is actually a solution to this differential equation. To write a general solution for this equation, we need a second linearly independent solution. We would call that y2, and since we know one solution, x squared, for our second solution, the guess that you make to do reduction of order is that your second solution is the first solution, x squared, times some unknown function, u. All right, and then plug this into the original differential equation. To do that, we need to take some derivatives. So y2 prime is 2x times u plus x squared times u prime. Don't forget that u is a function of x, and so its derivative isn't 1, it's u prime. Second derivative of y sub 2 is going to be 2u plus 2xu prime. So that's the product rule for the first piece. Now the product rule for the second term here, 2xu prime plus x squared u double prime. And then simplify this. So 2u plus 4x times u prime plus x squared times u double prime. Now we can plug this all into the differential equation. So the original equation is x squared y double prime plus 2xy prime minus 6y equals 0. So putting all of this stuff in here, we get x squared times y double prime, so 2u plus 4xu prime plus x squared u double prime plus 2x times y sub 2 prime, so 2xu plus x squared u prime minus 6 times y sub 2, which is x squared u. This is all equal to 0. Now let's gather up all of our u double prime terms. So there's just one of them right here. So x to the fourth u double prime. Now let's gather up our u prime terms. There's one here and one here. So let's see, we have 4x cubed times u double prime. I'm going to factor out that u single prime. I'm going to factor out that u single prime here. So now for this term over here, plus 2x cubed, right? Don't forget to distribute these as we simplify. Okay, now for our u terms. So there's the 2x squared coming from over here, and then there's a plus 4x squared coming from here, and then minus 6x squared equals 0. And so when we worked out reduction of order for the general case, what we saw is that this term with u should cancel. And we see here that it does, right? All of this stuff in parentheses adds up to 0. And this is a nice little check. If you're working out reduction of order and your u term doesn't go to 0, you made a mistake, and so you should back up and fix it. Okay, so this leaves us with x to the fourth times u double prime plus, let's see, 6x cubed u prime equals 0. All right, now this is supposed to be a first order differential equation in u prime, and it is, right? There's no u here, so this is a first order equation in u prime. If we want, we can replace u prime with w. So u double prime is w prime plus 6 times x to the third times w Okay, now we need to solve this equation for w. It's separable or linear, however you want to work it out. So let's maybe move this to the right and then divide by x to the fourth. So w prime is minus 6w over x. And then separate, so dw over w is equal to minus 6 over x dx. And now we can integrate. Natural log of w is equal to minus 6 natural log absolute value x plus a constant. Now, in our first example, we saw this constant isn't really important for what we need, right? We're looking for a linearly independent solution, a solution that's linearly independent from y sub 1. And this constant sort of just tells us that y sub 1 is a solution, but we already know it's a solution, so we actually don't care about this constant for this particular situation. So now let's finish solving for w. So exponentiate absolute value of w is, I guess it's going to be absolute value of x to the minus 6th. So w is x to the minus 6th. Okay, remember w was u prime. And now we need to find u. U is, so integrate, we get, actually, you know, why don't I keep this constant? When we exponentiate, we get an arbitrary constant here, 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 and it's a multiple because of exponentiation. Okay, so now when we integrate, we get arbitrary constant times x to the minus 5th over minus 5 plus another arbitrary constant. Now this is the one that recapitulates the fact that y sub 1 is an arbitrary constant, or that y sub 1 is a solution, so we don't actually need this. And also, right, what we're looking for is just some function u that will work. And we can choose any value of a, except for 0, and get a function for u that will work. So what we should do is choose a so that this is as simple as possible. And if we choose a to be minus 5, then u is just x to the minus 5th. All right, so now that we know u, we know y sub 2 is y sub 1, which, what was y sub 1? X squared. Okay, so y sub 2 is x squared times u. But now we know what u is. It's x to the minus 5th. And so y sub 2 is x to the minus 3rd. So now that we know y1 and y2, we can write a general solution. It's some constant times y1, which is x squared, plus some constant times y2, which is x to the minus 3rd. And there we go. There's a general solution to that differential equation.